Let's continue our discussion of random variables. There are parameters for random variables, that is, measurements for this random variable. We talk about mean and standard deviation, mode, median, those sorts of things. The mean of a random variable is also known as the expected value. So in the long run, what would we expect to have happen? That's what expected value is. It's the sum of each data value times its probability. Sigma squared, you hopefully remember that as being the variance of data. So the variance of x is equal to the expected value of the data squared minus the expected value of the data quantity squared. In other words, the sum of the x squared, the data value squared times its probability, minus the mean value squared, because mean is expected value. The mode is simply the value with the highest probability. Not that strange. Whatever's most likely to happen is going to most likely happen the most and be the mode. Well, let's look at an example. Find the mean standard deviation for random variable x if random variable x is the number shown when a die is rolled. Okay, so what does our probability distribution look like? Well, what values can our random variable take on? 1, 2, 3, 4, 5, or 6. And if this is a fair die, and unless we're told otherwise, we're to assume that it's a fair die. So each of these have probability of 1/6. So for our mean, that is our expected value of random variable x, we're going to take each data value and multiply by the probability. And through this fairly straightforward calculation, we get 21/6 as our mean. Not terribly difficult. In our calculation for the variance, well, that's the only formula I gave you. I didn't give you a formula for standard deviation, but what you have to remember is that standard deviation is that symbol, whereas variance is sigma squared. So find the variance and then square root it. And remember, this formula was the expected value of x squared minus the mean squared. So we need the expected value of x squared. It's going to look similar to this, except all of these data values will be squared. So we're going to have 1 times 1/6 plus 4 times 1/6 plus 9 times 1/6 plus 36 times 1/6 for a total of 91/6. So our standard deviation is going to be the square root of 91/6 minus the mean squared. And if we reduce the mean to help us with the calculation, do the calculation a little bit better, we see that it's 7/2. So 7/2 quantity squared, we end up with the square root of 35/12, which is approximately 1.71. New problem. We're going to play a game. Tom tosses 3 coins. He wins $9 if he gets 3 heads, $5 if he gets 2 heads, and $2 if he gets 1 head. If he gets 0 heads, he has to pay $30. Is this a fair game? Is this game not biased in favor of whoever's putting the game on? And similarly, is it not biased in favor of the person playing, because both of those are examples of unfair games. Fair game, both the player and the person you're playing against have equal chances of being successful. So for this, we need to look at the possible outcomes. We need to examine this probability distribution, and we want to find the expected value. So we need to list out the possibilities. Head, 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 and so on, all the way down to tails, tails, tails. I'm confident you can find all 8 of these possible outcomes in this experiment. And if it helps, use a tree diagram. It'll help you not to miss anything. So what's the probability that A equals 9, where A is the amount 1? That's our random variable. Our random variable can take on a value of 9. Well, that's only going to happen when we get all 3 heads. The probability of that is 1/8. All of these outcomes are equally likely. What's the probability that A could be 5? 5 would be another value that A can take on. Well, there are 3 total outcomes with 2 heads, so our probability is 3/8. What's the probability that A is 2? And we find that this is also 3/8, and we might think we're done here. But this is not a probability distribution. Although these probabilities are all between 0 and 1, these do not add up to 1 yet, which means we're missing something. And we're missing the one where they're all tails. Well, what's the value of our random variable there? Well, the value of our random variable there is -30. He loses 30, and the probability of that is 1/8. To examine if this game is fair, we are going to find the expected value for A. So we're going to take each value for the random variable times its probability. And what we find here is that this is 0. So in the long run, it's not expected that Tom will win, but it's also not expected that the person he's playing against will win. It's expected that they'll come out even when it's all said and done. That makes this game a fair game. Last thing we'll look at in this video is something called a cumulative distribution function, also again called a cumulative density function, and it's abbreviated CDF. The CDF of a discrete random variable x is f of x, where f of x is the probability that x is less than or equal to x. So we're talking about, when we say that we want the CDF for 5, we're referring to what's the probability that the random variable is 5 or less. And we get that by adding up all the probabilities for the values that are less than that value of x named. So the median of f of x is defined to be x1 plus x2 divided by 2. Got it right there. And x1 and x2 are read off of our cumulative density function, off of our table. x1 is the smallest value, it's the maximum value for which the probability is less than 0.5. And x2 is the minimum value, it's the smallest value for which the probability is bigger than 0.5. And that will make a lot more sense when we do this example. So we're going to construct a cumulative distribution for the random variable x, where x is the number of heads when 2 coins are tossed. And we have a probability distribution right here. This is a very simplistic one. There's only 3 outcomes. We can either have 0 heads, 1 head, or 2 heads. and the probability of each is 0.25, 0.5, and 0.25. The cumulative density function of x, the first value would be 0. That means what's the probability that x is less than or equal to 0? Well, that is 0.25. The next value that we would put is 1. And when we say 1 for the random variable in a cumulative density function, we're saying what's the probability that x is less than or equal to 1? So we have to take both of these two and add them together. And finally, when we say 2, we're saying what's the probability that x is less than or equal to 2? So that means we're going to add this onto it for a total of 1. When you look at a cumulative distribution, the last value should always be 1 because that last value represents every possible thing that can happen in that experiment. So the question becomes, what's the median? I said it was x1 plus x2 divided by 2. Well, what's the biggest x value that's less than 0.5 for the cumulative probability? Well, it's 0. What's the smallest value for x that the cumulative probability is greater than 0.5? Well, that's going to be 1. So our median would be 0.5. And that is where I shall leave you today, ladies and gentlemen. In the next video, we're going to look at a very specific probability density function known as the binomial probability. It is a wonderful, exciting time. I hope you're looking forward to it. Have a blast.